Good morning, class. This is Tim Tomlanovich. Welcome to Structural Analysis 2 again. This is Learning Plan 2, Chapter 5, Part 2. So we're going to continue going over, and you should have enough information to get your homework done. So with that, I'm going to just get some things set up here. All right. So what I'm going to show you is how to calculate deformation of building materials from force systems. Okay, again, I have a lecture sheet, so this is Structural Analysis LP2 Part 2, so you should see the LP2 Part 2 lecture note sheet. Excuse me. So, elasticity, strength, and deformation. So, basically, from Part 1 lecture, when we have stress in a structural member, we also have strain. So those two are interrelated, like I said, are related. So if we don't have any strain, if we don't have stress, if we don't have stress, we don't have strain. So when you look, and we have compressive stress, we squish it. We have tensile stress, we pull it apart. We have compressive strain, it gets shorter, that change in length is shorter, and then if it gets longer, it's tensile strain. So those are two related, okay? So if we look at this, if we unloaded, we don't have, see, remember that's that delta term right there. That's that delta term. So if I look right here, so that's my delta. That's that change in length, okay? So now all of a sudden, a steel bar under tensile load. Once I put a load on it, I create one tensile stress, normal stress, and I also create tensile strain. And there's that delta again, okay? So depending on the load, as you can see here, twice the load, twice the deformation, okay? So and then sometimes when we get too much load, we get 3 times the deformation. So basically what that's saying, it's not proportional. So that's where we're going to talk about the term of elasticity. Okay. Basically elasticity, think of it as a rubber band. When you stretch a rubber band and you let it go, it comes back to its original shape. It's elastic. Okay, but there's a point when you stretch that rubber band too far, will not come back. All the deformation will not disappear. So and that's what's happening in this case right here. So we have too much stretch, too much tension or compression, and then when the load comes off, it does not want to rebound back. The deformation does not disappear. Some of it stays there. So this is an important design concept in wood, in steel, in soils. Okay. So there's something called the elastic limit, is the maximum level at which no permanent deformations result from application and removal of a load. If this limit of loading is exceeded, a permanent deformation results. The behavior of a material is then termed as plastic or inelastic. So remember that last lecture we had that Fy, the yield stress of steel, was 50 KSI. So basically that is the point when we go from the elastic limit to plastic deformation. Okay. So when we look here, we have stress, KSI. Remember, that's unit stress. So unit stress is similar to normal stress. The load is perpendicular to the surface area. And then we have unit strain. Okay, the load is perpendicular to the area. Okay, so as you look here, as I get stress, I get a certain amount of strain. Remember, strain is a unitless number. So as you notice, this is a linear sloped line. Okay, and then all of a sudden, what happens here is it starts deforming. See, it starts yielding. So the load doesn't increase, but it starts deforming, and we get something called strain hardening, and also we have an ultimate stress, and then it ruptures. So you can kind of see these are the stress strain diagrams of different materials. Okay, so let's analyze this stress strain diagram in detail here. So point A, so basically from here, from point 0 to point B is called the proportional limit. Okay, so that's basically when things are proportional. So for the equal amount of stress, we get the equal amount of strain. So it's proportional. That means the slope of this line from 0, 0 to point B is constant. This is literally a slope of a line. So that is the proportional limit. Okay. And then A is an allowable. So that's when we have a factor of safety, because we do not want our allowable loads. So when you see those tables, design guides, codes, basically the allowable stress or the allowable load is in this elastic limit, because we don't want to be close to the yield limit, because if we're close to the yield limit, we're going to start getting deformation and our structure is not going to be serviceable. We're going to start getting settlement, windows are going to start cracking, things are going to deform. Okay, so basically what's going to happen is if that load comes off, it'll come back. A perfect example is the Leo Frigo Bridge. So if you remember, 5, 6, 7 years ago, the Leo Frigo Bridge, one of the towers settled. So what happened there? It was not a bearing capacity failure. It was a structural steel failure. So what happened was due to the organic soils by the Fox River, the water and the fly ash being there, it created a very corrosive environment. So what it did was erode the cross-sectional area of the steel piles on the pile cap, and then that load on top of that steel pile cap exceeded the allowable stress. So if we remember what stress is, and this is equals force divided by area. So that load was that tower, okay? What happens to stress when the area gets smaller? When I do math, when area goes down, the stress goes up, and then what had happened was it exceeded the allowable stress. It deformed. Okay, so that's what happened in that Leo Frigo Bridge. So what they had to do, okay, and then if you remember, the horizontal steel beam that's holding up the highway was actually deflecting. However, due to this situation, that deflection stayed in the elastic limit. So that's why they didn't have to tear this up, that bridge deck apart. They were actually able, it stayed in elastic limit. So when they jacked it back up, it went back straight. We did not have any permanent deformation. They did some calculations that we're still in the elastic range. So it's a very interesting phenomenon. Okay. So basically, so that's the proportional limit. And then C is the upper yield and D is the lower yield. So this is what happens in steel. You get an upper yield and a lower yield. It has to do with the manufacturing of steel. I don't know the details, but as you know, just remember the upper yield is the point when we start getting plastic deformation. Okay? And then as it get a lower yield, and then as you can look here from point B, once you look at it, it says elastic range, and then from point C all the way to basically here is the plastic range. Okay, and then from here to here is called strain hardening. So this happens in steel. What happens is it's very interesting, because steel is manufactured, it's melted metal, iron, okay? And as steel starts deforming, the chemistry, the molecules start changing shape, and it actually gets hard again, okay? So that's why they call this strain hardening, and all of a sudden, it'll start failing. So the ultimate stress, that's when it just starts failing. And then there's a point when all of a sudden the cross-sectional area is so big it actually breaks. Okay? So what happened to the Leo Frigo bridge was it went from point C to point E in a matter of a few hours. Because what happens is I'm guessing it started doing this, but nobody could notice it. And all of a sudden, it kept doing that. It started deforming, but nobody noticed it driving over the bridge. And all of a sudden, it went boom. And that's when it finally just went, it dropped. Okay. So that's the rupture point. So that's literally it breaks. True rupture means that's different because remember, as we stretch things or compressing, and when you stretch things, the area gets smaller. So that's based on this formula right here. Okay, so that's a little background on engineering of steel. Okay, so because of that, we know we can create the modulus elasticity of materials. E equals the modulus elasticity, and that's stress. Its slope of this line is stress over strain. So remember, stress is P over A, and strain is deformation over original length. And that determines our modulus elasticity. And that's an important design property. So when you look at Doug fir here, see it's a lot smaller than steel, aluminum. Every material has its modulus elasticity. So you need to find that from design manuals. Okay. So if you look at this table, this is in your book. You have different materials. On the left side, you have a unit weight, pounds per cubic foot. You have a modulus elasticity. So here's wood. You have different modulus elasticities. They actually test it. You have allowable tension stress, capital FT tension, allowable actual compressive stress, allowable compressive bearing. Okay, see this says perpendicular. Perpendicular. That means perpendicular to the grain. This is perpendicular, or this is parallel to the grain. So let's talk about this. So let's look at steel. Do you notice the tensile stress and the compressive stress are exactly the same? They are in steel because it's manufactured. The same properties. It doesn't matter if I'm squishing it or pulling it. The properties are the same because we manufacture it. However, if you look at wood, if you look at the allowable tensile stress of Douglas fir larch north, it's 650 pounds. However, the compressive stress is 1,000 pounds per square inch because that's the way the way trees grow. Okay, trees are stronger in compression, lumber, than tension. Okay, so, and this is assuming parallel to the grain. That's why when you look at floor joists, when you look at lumber, when you look at a floor joist, the grain is running horizontally, okay, because it's stronger in that way. So when you have a load perpendicular to the grain, you see it's even weaker. So this is when you're perpendicular to the grain. So let's draw a picture here. So I have a floor joist here, okay. So here's my wood grain. So when it says compressive stress of 1,000, I'm parallel to the grain. So if I'm squishing that floor joist and basically a column, if I just take that column, right, and turn it, that'll turn into a column. This is 1,050 psi. Okay. However, my load, sorry about that, my floor load is perpendicular to the grain. Okay, so now it's 625 psi is my F bearing, P allow. Okay, so it's important. So like you say, columns, right? The grain is this way. So we use FT and we use FC. Okay, floor joist we got to use perpendicular. So it's very important that you distinguish those two, that you understand the orientation of your grain. In wood, steel, it doesn't matter. Okay, and you have the same thing with glue-lams and parallel beams. Okay, and then you have concrete, stone, brick, so kind of the same principle. Okay, so that's in the US units. Same things are in the metric units, so I just thought I'd show you that. All right, so how do we calculate deformation? So if we know the modulus elasticity, which is stress over strain, we can rearrange that equation and find delta. So this is a very common formula. I want to know how much deflection I'm going to get in that column, that footing, that deep foundation, that tensile rod, etc., etc. So by rearranging this equation, knowing stress and strain are proportional, they're related to the modular elasticity, doing some algebra, we know delta equals PL over AE. I remember this as FLE or PLE. Let's remember PLE, PL over EA. It doesn't matter if the A and E are switched because multiplication property. So PLE, PLEA. So deformation in inches, actual load in pounds, length in inches, cross-sectional area member in inches squared or millimeters squared, modulus elasticity, PSI or KSI. So if I report my modulus elasticity in KSI, my load better be in kips. If my deformation, I want my deformation in inches, my length better be in inches. If I want my deformation in feet, my length better be in feet. Okay, so it's very important. Cross-sectional area, same thing. Deformation in inches, we need inches squared. So make sure your units are consistent, otherwise this will not work out. Okay, so with that, let's do some examples. Okay, a vertical 6x8 S4S timber column of Douglas fir is 10 foot 6 tall and is subject to a compressive load of 30,000 pounds. Calculate the unit stress and the total shortening, right, because it's being shortened, that occurs under this load. So let's define our variables. I am stuck on my cords here. Okay. P equals 30,000 pounds. So start defining your variables. Okay. We have a 6x8 S4S. Okay, surface on all four sides. So is that a true 6x8 or is that a 5.5 by 7.25? So where can I find that? You can actually find that in tables in your book as soon as I find it. It's somewhere in your book here. It might be in the appendix. It has a nice table here of S4S. Dimensional lumber here. Let's see if it's in the back here. Wood. Yes. If you go to page 567 of your book, appendix A1, I need to know the actual dimensions, okay, of a 6x8 S4S. Okay. So if I go to table A1-B, a 6x8, a nominal 6x8, because they say nominal, right? You go to a lumberyard, you call it a 2x4, but you know it's actually 1.5 inches thick by 3.5 inches wide by so long, right? So it's important that you understand. So we don't want to calculate the area 6x8, which is 48 square inches, versus the actual dimensions. My area is actually smaller, so my stress is going to go up. Okay, so 6x8 nominal, and surface dried size is, if I look here, is actually 5.5 inches by, is actually 7.5 inches. So you pick that off from lumber tables. And the nice thing about this table in page 567, it calculates my area. It calculates the area of surface dried size actual. So it's 52.25 square inches. So area equals 52.25 square inches. Okay? My length, so I have my load, I have my area. Now my length equals 10 foot 6 inches, which equals 10.5 feet, which equals, so there's 12 inches per foot, right? I gotta find my calculator here. Guess I'll just use my phone. All right. So 10.5 times 12. That's 126 inches. Okay. So my length, P, A, length. Okay. Question 1. It says calculate the unit stress. Remember, unit equals normal. The load is perpendicular to the surface area. So unit stress. So FC equals P divided by area perpendicular. And that equals 30,000 pounds divided by 52.25 square inches. And that equals, okay, 30,000 divided by 52.25, 574.16. I'm going to round it up to 575 pounds per square inch. Okay. So first thing you want to do is my load, does that exceed my properties of Douglas fir larch? So my grain, right? My grain is this way. Okay, so when I go back to the table, Douglas fir larch, beams and posts is probably a number 1. My modulus elasticity, we're going to need that value anyway. Allowable tensile, allowable compressive stress parallel to the grain is 1,000 psi. Okay, so this is less than 1,000 psi. We're good, because remember that 1,000 psi is in the elastic zone of that modulus, that slope of that modulus elasticity. So we're okay. Now it's asking us shortening. Okay, so that's delta equals PL over EA. We know we have 30,000 pounds times 126 inches divided by my modulus elasticity. Where do I find that? From the chart. That's the metric. Don't get them confused. All right. Douglas fir larch. So does it tell us what kind? Let's just look here. Oops. Column. Okay, so it's a column, so it's probably a number, beams and posts, number 1 there. So my modulus elasticity is 1,600 KSI. So we got to get that in pounds per square inch. So 1,000 or 1,600,000 pounds per square inch times my area, which is 52.25 square inches. So now it's order of operation. Okay. All right. So we're going to take 30,000 times 126. This is what I like to do. So that's 3,780,000. 3,780,000 divided by, so 1,600,000 times 52.25, and that equals 83 million. So if you have a nice calculator, you just have your numbers, recall your numbers in your calculator Okay, remember you got to multiply this times this, divided by this times this, or you can take this times this, divided by this, enter, divided by this, enter. It'll give you the same answer. Okay, so 378,000 divided by 83,600,000. 83,600,000. And I get 0.045 inches of shortening. That's not a lot. So if you take that number, just turn it into sixteenths, take it times 16, so that's less than a 16th. So it's about 1/16 of an inch of shortening. That's not much. Okay? So that's example 1. All right? So, okay. So we answered this stress, and then we answered the shortening. All right. Example 2, 5.12 in your book. I am on page 282. I'll read the problem out loud to you. It says, determine the allowable load capacity of the column shown, assuming that the allowable compressive stress, FC equals 600 psi, accounts for the buckling potential. And we'll talk about buckling later in the semester. Refer to standard wood tables in A1 of the appendix for information on cross-sectional properties. So when I look at the diagram, it's a 4x4 S4S, Douglas fir larch. It says determine the allowable load capacity. Okay. So F prime C equals load divided by cross-sectional area perpendicular. Okay. However, we're going to conform this. We're going to go FC allow, the allowable stress. These two terms are interchangeable. Okay. Because now it gave me an allowable stress, but it's the same formula. Equals P divided by a perpendicular. Okay, so the question is asking allowable load capacity. Okay, so now if I take FC allow times my area perpendicular to the load will equal P, which, because I'm using my allowable stress, I'm calculating my allowable load based on that area, so I do not exceed that stress. Okay, so you can call this P allow. So basically what we do when you're calculating the actual stress that is on that member based on your load tracing and your dimensions of your structure, and then you're checking it against factors of safety and allowable. Okay, so this is typically how you would design it. Okay, I want to use a Doug fir column. Okay, this is the area that I can use, right? This is a remodeling project, and then does my load exceed, my existing load exceed that allowable load? So you're checking it back and forth so you can rearrange that equation. So we know FC allow equals 600 pounds per square inch, or that's PSI. And we know our area. So it says 4x4 S4S, and I do believe that's 3.5 by 3.5. I'll just double check. I go to page 576, 4x4. Yes, it's 3.5 by 3.5, and the area is in 12.25. So when you're looking at this table in the appendix or any of these tables, make sure you're looking at English units or metric units, because they have both on there. Don't get them confused, okay? Make sure you're looking at the right column. So area is 12.25 inches squared. So now we can solve for P allow. P allow equals 600 pounds per square inch, and I'm going to multiply that by 12.25 square inches, and that'll give me my allowable load. So 600 times 12.25, 7,350. That's a comma, pounds equals P allow. Okay, so if I just number the steps here, this is my formula. I'm reading the problem. It's asking me to find the allowable. So literally I rearrange the equations. I define my variables and find the solution. So basically, so now this problem, I can only, to not exceed 600 pounds per square inches, my load can't be greater than 7,350 pounds. If it is, or I'm going to exceed that, that means what do we have to do? We have to either use a bigger post or a different material. Okay, we got to change one of these. Reduce this or make this bigger to reduce that, to get it less than this. This is your key number right there. Okay, so how this kind of critical thinking. What happens if this load, if I put load, this P back into here, I get 600, right? But if this load gets bigger by the same area, this number gets larger, so then it's exceeding that. So you have to figure out what situation you're in. Can I reduce the load? Do I have to make the member increase the area to reduce the stress, etc.? Okay, so this is the design. Oops. All right, example 3, 5.14. I'm on page 283. It says a heavy chandelier weighing 1,500 pounds. So as I'm reading this, that's a P, right? Chandelier, so it's hanging, so that means we're in tensile stress, right? P equals 1,500 pounds. Okay. Is suspended from a roof of a theater lobby. The steel pipe from which it hangs is 20 feet long. So L equals 20 feet. Might as well get that in the inches right away, times 12 inches per foot. So I just wanted to show you that inches cancel out because we have inches in the denominator here, inches in the numerator there. We're left with pounds. So unit conversions. Just make sure so if you don't really have to memorize the units of what that is. The units work themselves out if you do algebra. Okay, so 20 times 12, can't do that in my head. 20 times 12 is 240 inches. Okay, determine the size of pipe necessary to carry the chandelier safety. Use A36 steel. So we're using A36 steel. So that means Fy equals 36,000 psi. So they have different, steel has different terminology. A36 steel basically means Fy equals 36,000. What is the resulting elongation of the pipe? Okay. So it's asking us to find, okay, first we need to find, let's see, what is it asking us to find? It's asking us to find the area to hold 1,500 pounds, that's 20 feet long, and then it's asking us to find the resulting deformation. Those are the two things, okay? So, knowing, so stress, and T stands for tension. So we're not talking about shear stress, we're just talking about normal stress or unit stress, equals P over A. Okay? So, how do we know? So we're going to turn this into, because it's because it is a 30, they told you use A36 steel. So if I go to A36 steel, Fy equals 36,000. The yield stress equals 36 KSI. So I apologize if I'm confusing you from before. I go to on table 5.2 on page 278. Allowable tensile tension stress, FT, is 22 KSI. Because remember, we have to get in that factor of safety. We got to get back down in the elastic range. So 36 KSI is when it yields, but we need a factor of safety on that. So we know by looking at the table 5.2, FT, I'm going to turn that into a capital F because that's a design value. Allow, I like to put allow, it just that's telling me that I'm looking at design tables, equals 22 KSI or 22,000 PSI. There's 1,000 pounds per kip, so I just add 3 zeros. Okay. So knowing that, now what we're going to do is we're going to say FT allow equals P over A. Okay. Now we want to solve that equation. So P, we know the load on these two basic algebra, these two switch spots, divided by FT allow equals my required area. Okay? So let's do that. So this is step 1, step 2, step 3. I'm just to help you out here. 4. So when you're doing your quizzes, if you do this, you then I can follow. Okay, you're looking at this, and then I'm moving through the calculations here. Okay, so equals. So now we're going to solve for it. So P is 1,500 pounds. Whoops, LBS divided by 22,000 pounds per square inch. Okay. The pounds cancel out, and we're left with square inches, and that's an area term. So I'll do that calculation. 1,500 divided by 22,000. So remember, like units, 1,500, 22,000, or that is 1.5 kips, and that's 22 KSI. Make sure your units are consistent. So 1,500 divided by 22,000, I get an area. I'm going to call it area required because that's kind of what we're looking for, right? Equals 0.06868 square inches. That is the area of steel. Now, is that solid steel or is that a hollow pipe? It doesn't matter as long as I have that much area. Okay, so now what we're going to do is we are going to look at the tables in the back because we need to find steel pipes. So let's see here. So if you go to the back of your book, let's see, say 567 is lumber. Let's see, what's this? Beams. So you should have one for, I got I-beams, flanges. All right, pipe, dimensions and properties. So I am on page, well, that's all metric there. I am on page 574 of your book, and I'm looking at the pipe dimensions, okay? All right, it's A36 steel. So I need a cross-sectional area. So you find the area, it says properties, area, inches squared. So I need to find an area at least 0.068 inches squared. So when you hit the first uh, row here, we're using a nominal diameter of half inch, wall thickness 0.019, standard weight. The area of the steel is 0.25 square inches. So I'm using a pipe. Select half inch pipe. So that's my nominal. So when you say nominal diameter, I want a half inch pipe. Outside diameter is 0.84, inside diameter is 0.62. You subtract the two, you get the wall thickness, and then you use the wall thickness to actually calculate the area of the steel, which tells you, it gives it to you, which is 0.250 square inches. Okay? Is this number has to be less than that number. Okay? So again, I'm finding this on page 574, pipe dimension and properties. Okay? So now we want to check, okay, 3, 4, 5. So step 6, we want to make sure our load, 1,500 pounds, divided by 0. Because that's the area that we selected, equals 1,500 divided by 0.25 equals 6,000 psi. That is our actual stress. This equals F tensile stress actual. Because that is we selected a half inch pipe bar. That's my actual stress from that load, and it's 20 feet long, and that is less than FT allow. It's always good to go back and check, because what happens if this area is smaller, we're going to exceed this. Okay, so we're good. That's awesome. All right, let's do 7. Now we got to find, based on that area, it's asking how long will that thing stretch. So because it's steel, it stretches in compression, so we go delta equals PL over EA, and that equals 1,500 pounds. It's 240 inches long. Remember, we got to stay in consistent units. The modulus elasticity of steel, A36 steel, is 29,000 KSI, or 29 million. So 29 times 10 to the 6, that means I add 6 zeros at the end of that. PSI, the units all cancel out, that's why we end up with inches, times, what's our area? We're using 0.25 square inches. Okay, so I calculate that out. So 1,500 times 240 equals, okay, sorry, that's a 4 right there. Sorry about that. This is 240. I'm going to divide by 29 million. Whew, there we go. Equals, and I'm going to divide by 0.25 equals. I get 0.0496 inches times 16. Oops. Okay. So I'm just 0.49 times 16. Yeah, I get about a 16th of an inch, less than a 16th. So that's how much deflection I get. Okay. So area, we answered that question. That's this guy. What's my deflection when it's 20 feet long? Okay. So you kind of see how those problems go back and forth with each other. Simple. You just literally using this equation and this equation. Just rearranging it, understanding is it design, is it allowable, is it actual? So that's the difference. Okay. So with that, that is the end of this lecture. So thank you. Here's your homework, and then if you have questions, you know when I'm available via WebEx. So have a great day. As soon as I figure out how to turn this off, I will let you know.